Kia ora, everybody, and welcome to this interactive and collaborative webinar on advanced thermal solutions for walls. Thank you all for joining us. There's more people slowly entering the virtual room, but we'll crack on and get underway. We have got quite a packed program today, and we're going until 12:30. So there won't be a break at any stage during this, so just look after yourselves and make sure, those of you that are joining us from home, that you've got handy supplies of tea and coffee and all of that on track. If you need a toilet break or any of that stuff, I would really recommend doing that in between speakers as we swap from one speaker to the other. Okay, I'm just going to start my screen sharing here. Okay, so hopefully you can see the Advanced Framing Solutions webinar screen up there. This is our program from the day. So we've got from 10 till 12:30, as I say. You can see it's quite tightly packed. We've got a lot of speakers there. We want to make this as interactive as possible. So importantly, throughout this, we're going to have the speakers speaking for around about 15 minutes each, and then we'll have an interactive Q&A session. And I'll talk to you about how you can interact with us as part of that. You know, ideally we would have been doing all of this in person, but as you know, with COVID, just the uncertainties around that and booking venues under level 3 in Auckland or level 2 was tricky. However, there's some real advantages, I think, as well in running this as a Zoom webinar. One of those are that we do get to get people from all across the country joining us, and indeed we have got people from the South Island and everywhere else, and they haven't had to have a large carbon footprint to get here. So really good regional access for them and a lower carbon footprint. Also, one of the other benefits is this will be a recorded session. So we are recording this and it's going to be available to everybody following this webinar, which I very much see this as not necessarily the start of the conversation, because people have been discussing these issues for a long time, but really a focus point of the conversation in New Zealand about how we can collaborate to find much better solutions in the space of thermal bridging and what we do with advanced framing solutions for this country. So that's one of the real advantages of Zoom, is this record ability. I'll just give you a brief rundown because we're not all in the same room, but we've got nearly 100 people registered for this webinar. So we've got people from MB there's 3 or 4 of them attending and really interested in the results of this. We have 3 or 4 people from brands here, again, very interested in this, and this is part of a brands research levy funded project, so it's great to have them here too. We've got a large industry contingent, so if you were able to look around the room, you'd see designers, engineers. We've got lots of people from the Frame and Truss Manufacturing Association and the Frame and Truss industry here, which is great to have them represented here, a really important part of this industry. And then loads of suppliers, insulation providers, cladding suppliers, those sort of people. So a really good range of highly experienced technical people in the audience all around you. And we really thank you for taking part in this. I think that's it for the kind of the housekeeping side of this. As I say, take a break when you need to in between speakers if you can. So what I'm going to do is just provide you with a little bit of a context of where we are in terms of today's workshop, and then we're going to go on and hear from the other speakers who bring some really innovative, I think, solutions to framing situation in this country. So I'll just provide a bit of context around thermal bridging and timber frame walls in New Zealand from some of the research that Beacon's undertaken. Now, most of you were sent links to this report that Beacon has recently completed, looking at the extent of thermal bridging in timber frame walls in New Zealand. And if you haven't had a chance to look at that, this provides a bit of a synopsis, but there's obviously a lot more detail in the report. So I'd really promote that, going and having a look at this report, ER53, easy enough to search just in Google by putting ER53 thermal bridging, and that will come up for you. And you can download a copy of that report from Brands. But as I say, this was funded by the Building Research Levy, and this is part of an ongoing project which we're involved with at the moment, with aims to really look at getting some insights into the scale of this issue of these high percentages of framing we're finding in the New Zealand residential construction sector, the effect that those high percentages of framing have on thermal bridging and as built, as constructed R values, and then the causes and reasons why that high percentage of framing might be occurring. So we're also really key and interested in exploring pragmatic and buildable solutions. And that's really what today mostly is about. How do we explore those solutions to these issues? So this started with a research project, and in terms of methodology, what we did is we took a case study approach of 47 newly constructed houses from Auckland, Christchurch, Wellington, and Hamilton. So we got a bit of a regional mix there, but it's important to note that this is not a representative sample. This is really just looking at a case study approach of some 47 newly constructed houses from those central markets. We utilised a combination of frame and truss elevations, which are very detailed images that come from the frame and truss factories, and then the wall panel layouts alongside on-site data collection. So we took those framing elevations and wall panel layouts and went on site and checked to see that all of the sticks of timber that were put in those panel layouts was actually what we were seeing on site, and then noting any additional timber that we'd found. We looked at a range of typologies, usually between 1 and 3 stories, and a variety of different builders, different companies, different developers, a range of different cladding types and so on. So again, not a representative sample, but we got a pretty good mix of different variables to look at in that. It's important to note also that frame and truss, and this was a finding that we weren't necessarily aware of at the start of this, but frame and truss have got a very efficient process, and they deliver to 95% plus of all houses in this country. So that's why it's been great working with them as an industry body, and they were really good at sharing some of these elevations. And I think they're also really engaged at coming up with some solutions about how we overcome these issues of thermal bridging. And they've been pretty fascinated in the results of the research as well. So in terms of those results, I'll quickly go over some of those. So we looked at 47 dwellings, as I said. That breaks down into 71 separate building levels and 1,103 individual wall panels that made up those separate building levels. So that is literally thousands of sticks of timber that were looked at and counted on site to come up with the results of finding out what these percentage framing ratios were. And in terms of headline results here, the average percentage of timber framing that was compared to that overall net wall area, so that's taking out doors and windows from the equation, is actually above 34% in terms of the wall makeup. The lowest that we found on a level by level basis was 24% framing in those walls, and the highest got up to 57, as much as 57% of timber versus the insulation that you might have there. So that wall really ends up being nearly 2/3 solid timber. There are a range of drivers for this that we've started to identify, and we're doing a bit more research looking at those, but it's everything from structure, NZS 3604 and the requirements around that, requirements around weather tightness, E2, cladding requirements as well from different manufacturers and different cladding types that we're producing. And then also design. You know, if you move windows and doors from a few millimeters to 300 mil, you might be able to get away with putting less timber. So there are ways of optimizing the amount of timber in our walls. And again, we're doing a little bit more research looking at how that might be done. One interesting thing to note was, despite what we had thought, there's actually little additional framing that's added on site. So the average across the household level was around 2%. So it wasn't a case of builders and plumbers and sparkies putting in lots of extra nogging or support structures in there. But there are also some really significant uninsulated areas. So the average there was 3%, but it could be as high as 10% in terms of area by each level. And these are areas where we simply can't get insulation in because of the way the house is constructed, and also the timing of those different trades and the insulation installers coming to site. In terms of a few key observations, well, obviously with that 34% average of wall framing, that's much, much higher than the 14 to 18% framing content that's generally assumed by regulations and by the industry itself. So nearly double what's that assumed. And that means that our construction R values are much lower than expected, and we're really unlikely to be getting the performance that we thought. And that's as a direct result of this thermal bridging, the framing levels that we've got, and then also the insulation install itself, both in terms of the quality of that install, but also how difficult it is to get into some of these uninsulated spaces. There's some distinct weak points and blind spots as well in this. So mid-floors, corner junctions, internal wall junctions, lots of these uninsulatable areas. And I'll show you a few pictures relatively quickly just to go through some of those as well. And not forgetting that some of the areas of the framing is highest in those cold, damp, condensation-prone areas. So that's your bathrooms, laundries, and I always think of the back of your south-facing cupboard, those areas that do tend to have a lower condensation dew point, and then therefore that's where mold starts to grow on the surfaces of those structures. Now, interestingly, as part of this, we also looked at the definitions provided by NZS 418, and the great people at Brands, particularly Ian Cox-Smith, did some work for us looking at this, the calculations that might come out of their R value calculator for walls. And this definition in NZS 418 states that you include the studs, dwangs, top plates and bottom plates, but you can exclude lintels, additional studs that support those, additional studs at the corners and junctions. So actually when you compare what actually goes on the wall, which is that picture there on the left, to what you're allowed to count in NZS 418, which is on the right, you can see there's a huge variation in what we're getting for that construction R value. We'll go through a couple of examples of those a little bit later. Just some field observations to illustrate some of those things I was talking about. Here's a picture of some uninsulated mid-floor framing. You can see a very large area of a thermal weak point across all of those buildings as soon as they get above 1 story. And that's almost never insulated in any of our construction. These corner details, again, none of the sample that we had showed any insulation being put into these corners. And this is actually taken from the inside. You can see the light coming through the corner of that building. Internal wall junction, so everywhere an internal wall meets an external wall, again, there's a void here behind this where these two walls meet, and we can't get insulation into that space. And here you can see from the outside, this large section that will remain completely uninsulated once this house is constructed. Very high concentrations of framing we found in various wall panels and across levels. This is a typical kind of scenario in a toilet. You can see the amount of excessive kind of framing going on there, or the large amount of high percentage of framing. And again, this is an internal wall, and you can see this corner here, just a solid wood block, which will be a huge source of heat loss. Stairwell blocking being added, again, this is for handrails here going up a stair, typically remain uninsulated in a lot of the spaces. And then several uninsulatable voids, which again are these spaces that we just can't simply get insulation into. We could go on and on showing you lots of pictures of the construction and the amount of timber that's in our wall, but have a look at the report. It's got a lot of detail in there, and that will really help you gain an appreciation for what's going on. But if I just very quickly look at these framing ratios, you can see this wall here, very simple framing ratio there of 28%, which would be one of the lowest that we would have found. You can see even with our insulation with an R value of 2 in there, we drop down to a construction R value of 1.75, and we need to get R 2.8 insulation just to get this R value up above 2. And when we get into higher framing ratios, here's one at 51% framing. You can see again with R2 insulation in the walls, that drops to R 1.39, and with an R value of 2.8, which is the maximum we can fit into this 90 mil cavity, we get down to just about that borderline R value of 1.51, which is the minimum requirement of 1.5 under E3. Okay, so these are real issues of real significance, and we really need a collaborative approach here to explore solutions. And that's really why we're running today's workshop. We're going to be exploring practical, cost-effective and innovative ways of constructing timber frame walls for improved thermal performance. The focus really is on pragmatic and buildable solutions that can be shared and widely adopted amongst industry using really familiar framing approaches. So it doesn't have to be new. We have to be able to share it and scale these up. And we want to highlight construction techniques that could be rapidly adopted with as few changes as possible to current regulation or compliance regimes, and as few changes as possible to what industry currently supply. So how can we be as smart as possible about this to achieve a much better thermal outcome? Okay, so thank you for listening to that brief overview. I'm going to hand over now to Guy Penny, who also took part in that research alongside the wonderful Jane Cumming, Graham Baker, and Ian Mays in that original project. Guy's going to run through some new modelling that we've just been undertaking to explore these issues in a bit more detail. He's a qualified scientist and engineer, 25 years experience in sustainability, and he's worked for a huge range of people. Most of you will know him in the audience, I suspect, across Aotearoa, and really interested in applied projects that help address social and environmental issues. So I'll pass over to you, Guy, and you can take us forward through the next presentation. Thanks.
Yeah, ngā mihi nui kia koutou katoa I tēnei ata. Good morning, everybody. Welcome to the presentation today, wherever you are in the country. Okay, I'm going to just run through some work we've done in this last year. We were basically looking at the construction system R values of as-built walls of residential properties. And these are preliminary results, and they are a project that has been funded by Brands and undertaken by Beacon. So just to sort of recap very quickly, the data for this modelling exercise is actually taken from our framing study that Vernie's just explained, that we did last year. The results of that were indeed quite interesting, where we saw 34% of timber in walls across houses, and we also noted 6 common weak points in the wall envelope. Now, in this particular study that I'm reporting on now, we take 5 of these properties and we calculate their wall construction R values, and we include the weak points that we've identified, and we also apply our SI values to our modelling calculations. So yes, this study that I'm reporting on today is we model a couple of different treatments, or several different treatments, based on the data that we collected last year in our wall study. So the first treatment, we look at these walls and we model with R2, R2.2 or R2.8 insulation fitted, and we've assumed that insulation is fitted perfectly. We then model those outcomes with the weak points resolved. So we want to understand what happens if we do actually deal with all these weak points. We then move on to, we model what it would look like if we drop the framing down to 25%, and then if we drop the framing down to 15%. And I would note that this process that we've been through has been, we've used Jason Quinn has helped us with develop our methodology, but we are getting our results peer reviewed. So the numbers that I report today may change, and to look out for the final research report sometime in the first quarter of next year, I believe. Okay. Just wanted to show you what different framing percentages look like on different wall panels. So the image on the left there is 15%. Sorry, 17% framing. Image there on the right is 25%. Obviously that has a lintel and a few extra trim studs and jack studs and the like. The image there on the left is 30% framing. That looks like it's at 400 centres possibly with the studs. There's a lot of timber around the edges. And the image on the right, that is 55% framing in that particular wall panel. So I just wanted to give you an idea what these percentages look like in practice. So to go to our results, when we modelled using R2 insulation. And what I'm reporting here is just from one house, because we're going through the modelling at the moment. We get R1.2. If we insulate with R2.2, we get R1.23, and with R2.8 we get 1.31. Sorry. Moment. If we then address the weak points in our modelling, we get slightly higher R values in terms of the performance, but they're not significantly higher. So that in that particular area there, we have addressed those 6 weak points that we've mentioned. Those are internal wall junctions, external corners, internal corners, losses through the floor plate and top plate, and a mid-floor area if it's a 2-story dwelling. If we then reduce the framing in this particular example down from 32% to 25%, our R values increase slightly again, but not a lot. We then reduce the framing down to 15%, our R values again increase slightly. And if we look at the case where we don't resolve the weak points, so we leave them as they were built, but we reduce the framing by 25% or 15%, we get those results there. So in all cases, on this particular example, we're not achieving anywhere near sort of R2. So in terms of our preliminary results, we can say that as-built walls of typical construction achieve a system R value of between sort of R1.2 and R1.3. If the common weak points are resolved, the walls achieve R1.3 to R1.45, and that's an 8 to 12% improvement, depending on what level of insulation you put in. If we then, on top of that, reduce the framing percentage to 15% of the net wall area, we achieve R1.5 or R1.8. And that's a further improvement of 15 to 25%. So a point to make, and Bernie made it earlier, is that the actual performance R values are likely to be less, as we've not accounted for the poorly fitted insulation. And our observations from our study last year and other observations on other studies is that poorly fitted insulation is fairly common. And we tended to observe this in sort of, I guess, 3 types of grade of installation faults, and some they were minor, moderate, and major, and that might be a way of thinking it in future if we want to somehow address these. But the question we ask is, how do we accurately quantify or model the losses from poorly fitted insulation? The conclusions that we can make, and again based on these preliminary results, is that we cannot achieve good wall system R values using the same design and construction methods and the same materials. And many parts of the wall perform below R1, which, as Bernie mentioned, also is below the E3 requirement for light timber frame walls. The thermal bridging through framing and other pathways is too significant to compensate for losses within the same wall design, and hence why we are having this workshop today. So how do we build walls with good system R values?
So
that is the end of the presentation. Thank you.
We have got a question there from Brian Berg. And he's saying, Kia ora Guy, is this modelling accounting for 2D heat transfer using tools such as Flixo or Therm? How do these results compare to NZS 4218 1D method? What's the effect of 2D heat loss transfer at this higher framing ratio and insulation levels? Thanks, Brian, for your question.
Yeah, that's a good question. The methodology we followed was one that Jason and I worked on. It doesn't use any of those R-value packages like Flixo and so forth, those thermal modelling packages. I don't know whether it deals with the 2D issues and so forth you're talking about, and would have to talk to Jason about that. But as I did mention, we are getting our methodology peer reviewed, and we may indeed do some comparisons with 4218 as we go through the rest of our research, but I'm not sure what we're doing quite now. Jason, did you have any comment?
Yeah, so I pre-processed the stuff in Flixo to take care of those 2D effects, and then provided those to you. So you did yours for the international method of, I guess it's ISO 6946, which gives results fairly similar to 4218, and it takes into account those 2D effects. So in the background, I pre-processed stuff in Flixo, and then provided those values for you, those psi values that you used along the lengths. So that's current international best practice, the methodology you've used, in my opinion, anyway.
Thanks, Jason. I hope that answers your question, Brian.
Yeah, thanks very much, Brian. We can follow up any of these questions later, or you can follow up with us as well if we haven't answered them in enough detail, but thanks for that. What we're going to do now is we're going to get started onto the other presentations we got. So thanks very much, Guy, for that. It was a really great set of emerging results, preliminary at this point. Still need to do a bit of peer review around those and make sure that the methodology is all good. Yeah, generally we're going to, I think, be finding some pretty interesting stuff out about just how those R values across those wall levels are affected by this thermal bridging. Right, what I'm going to do now is I'm passing over to Joe Woods and Shay Brazier of the Zero Energy House fame in Auckland. Now their house is a spectacular design, achieves good thermal comfort all year round without any active heating or cooling, very important to note in today's climate changing environment, and with little extra cost to build than a standard home. So I just know that their solution, which will come, I'm sure, with lots of lovely pictures of the home, is a good one that we should be looking at as a potential sort of front runner for this kind of design. So I'll hand over to Joe and Shay to take us through the Zero Energy Home.
Thanks, Bernie. I'll just try sharing my screen. So I'm just going to go through the framing system that we used on our house. I thought I'd give a little bit of, a context behind our building first. So we built in Auckland. Obviously the climate here is a bit different to the South Island. So the solution that we used here works for Auckland, but it might not work for everywhere in New Zealand. We were designing to achieve net zero energy. So we really wanted to minimize our energy use and offset the remainder using PV generation. And to do that, we really needed to achieve really good thermal comfort in the house and have no need for active heating or cooling. But we also wanted it to be affordable to build as well as operate. So these are our average temperatures in the house throughout the year. This is without any active heating or cooling. And as you can see, it remains reasonably comfortable all year round. Average temperatures don't get above 25 degrees and they don't get below, well, they just get to a little bit under 20 degrees. So that's average temperatures. So as you can see, it's fairly consistent all year round temperature wise, and it is very comfortable to live in. This was our annual electricity bill last year. So this was the total cost of our bill, including driving 15,000 kilometres. So we paid just over $1,000. So that included every energy use in the house as well as charging the car. But our total energy use over a year is typically just under 4,000 kilowatt hours a year. That's excluding our car charging. So that works out to be a little bit less than 20 kilowatt hours per square meter of the house area. This is the framing system we used. So it's actually pretty simple. It's very similar to the standard build where you have a 90mm frame and then a nog, but we've removed the nogs from our 90mm studs. And then we have an extra batten layer, which is 45mm thick. So the total wall thickness is about 140mm thick overall, but we've got a lot more area of insulation than timber in the actual build. So the picture on the right, you can see how it fits, how it works with the cladding as well. So the battens can actually run either inside the house or outside, inside the timber stud or outside the timber stud, depending on whether you've got vertical or horizontal cladding. So we actually have both vertical and horizontal cladding on our house. So we've got on some walls battens running on the outside of the stud, and on some walls battens running on the inside of the stud.
So I just add to there that just for those who aren't scientifically minded, the thermal bridging is obviously only where the battens cross the studs. So if you're thinking percentages, we haven't got the percentages unfortunately, but it'd be significantly less than without that approach.
Yeah, so it'd be more like a few percent rather than your typical, whatever the figures were in Bernie's presentation, which were reasonably high. So these are just a few images from the house when we were building it. So you can see on the left image, that's one of the external walls, which shows you the studs, and then there's the batten layer running on the inside. And as you can see, there's a junction coming up to a small internal wall here, which we've actually insulated. So when we were building, every little detail was insulated. It wasn't just about achieving this framing system. We also thought about insulating every little detail that you can't normally get to. So before the building wrap went on, all the little gaps were insulated. As you can see from the top right, one of the top right images, we've got the pipe runs that run through the batten layer. So because we've got the two layers of insulation, it means that we can run pipes through our batten layer and the builders aren't having to drill through any of the studs. The bottom image there shows our pipe runs. So it's probably not that clear from this image, but our large sanitary pipe runs were run inside the external walls. So they've actually built out an extra part to the wall so that they're not actually running in our main insulation layer. And that's actually really important because some of the sanitary pipes that you get are 90 mils, they're actually taking up quite a large part of your insulation layer. And then the top right, the very top right image there just shows you how the insulation was actually installed and how it went together. So as you can see, we obviously friction fit it and made sure there was no gaps. I mean, there's two pieces lifted up so you can see how the structure is there, but it was all neatly, the insulation was all neatly within the framing with no gaps.
And I can add to that too, that because you're not having to cut the insulation to fit in between the nogs, you can have a continuous piece of insulation that runs the whole length vertically between the studs or the whole width horizontally between the battens, which well, we'll talk about that a bit more later on, but,
yeah.
but conceptually can make the installation quite fast for the insulation.
I've put a few details in here. I won't go through these in too much detail because we've only got a limited amount of time, but this really just shows how we tried to manage insulating around all the different edges and corners and details that aren't normally insulated. So through all of our lintels, we've got two timber layers, but in between the two timber layers, there's a layer of insulation. And that's really important because often lintels get ignored and they just go in without any insulation at all. And then also just around some of the corners, we've tried to get as much insulation in. So there's, you know, minimal timber running through that junction and maximizing on the insulation and the thermal performance.
This one here is worth mentioning too. This is I think it's called balloon framing sometimes. So the studs run full height past the mid-floor. So this is the mid-floor coming in here, so the internal joist, the first joist attaches to the inside of the studs. So there's a full layer of insulation going past the mid-floor, which is unusual, I think, in buildings. And then this one here shows this, the bottom plate actually overhangs the slab, so that there's insulation below it. So that we can get that insulation and still get the overhang of the cladding. Next one. And I think that one's a fairly common internal wall junction, but just showing the fact that it's not just on the plans, there actually is insulation in that bit.
So I think Bernie pointed out in his presentation that that was an often missed place. So actually before the building wrap went on, the builders made sure they put a little bit of insulation in those little cavities there. So this image just shows the timber framing. We went to a pre-nail company to get our timber framing done, and the image on the left is the first set of pre-nail drawings we got back from them. This is how they do business as usual, and this is, you know, this is standard across the industry. And we ended up getting our architects to actually do our pre-nail drawings for us, because it was obviously very new to the pre-nail company. And there was a little bit of learning to do. There was 4 versions of the pre-nail drawings in the end. There was a lot of
4 reviews. So the 5th one was the final one after we got the architects to do the pre-nail drawings. It got to the point where we didn't feel like we were going to really get there with that process.
So there was a lot of backwards and forwards. But the image on the right is what we finally got from the architects. And as you can see, the orange lines highlight the extra timber that was put into the original drawings compared to the final drawings. This probably isn't the worst case that we had in our house in terms of business as usual versus what we actually had, but it was probably one of the clearer images we could show you today.
I think there's about 10 linear meters in that, roughly. So it's a reasonable amount of cost savings as well.
Obviously we've got this very simple timber framing solution, but the success of our build was also about the quality of build. All of our insulation was installed by us rather than builders. We wanted to make sure there were no gaps and no compacted areas. Often when you see insulation that's been installed, it is not that well installed, as Bernie highlighted in some of his images. The insulation was put in all of the gaps and cavities, so corners, junctions, lintels. We really paid attention to the detail. And we also chose a non-slumping insulation product, which we could easily friction fit, and where it wouldn't friction fit well, we made sure it was stapled or strapped in, so where we were using on the roof areas. So it was nicely secured in place, and we knew that when it was on the walls, it wasn't going to move.
Yeah, sure. So you know, our observation, you know, we're not a pre-nail company, but we're engineers and did look at this quite closely. Our belief is that this could be cheaper to build than a standard frame. And the reasons for that is that it uses less timber and less labor, even though it's thicker, to build a frame. So you're not having to cut nogs, nail nogs in, you're just nailing a batten across the top. The battens are 45 by 75, I think we use, rather than 90 by 45 dwang. So yeah, less timber. The insulation is less cutting, theoretically, if the frames are designed to fit the insulation width. So there's a lot less time involved in fitting the insulation. The cables and the pipes should be faster to fit because you're not having to drill through all the studs and then pull the cable through. You can just run it across the front and then push it up behind the battens to go up. We think it could be built equally easily on site or pre-nail. Obviously, if you can off-site fabricate, I would think that would be faster if you're geared up to do it. Although, as we'll talk about, and we have already talked about, really, that the pre-nail process currently is not really favorable to this type of construction. And while it could actually be favorable, it probably isn't right now. So I think with a fairly minor change over the standard construction, which was what we're trying to achieve, we think you could achieve significant improvements in performance. But the first time we did this, which I think helps to speak to the challenges that there are in moving to the solution, was that with trying to get it built by a pre-nail company that's used to building frames to a different approach and for different priorities perhaps, it was quite challenging to get the details that we required and that were on the plans. It's difficult to transport. We decided not to put the battens on at the pre-nail stage. We put them on site, which perhaps was a mistake, but part of that was to do around the bracing and be able to square it on site. There was additional cost for us in having the architects review and draw the detailed framing. Although having the architects do that, I highlighted that we probably could have done better with getting the window placements and sizes so they matched the framing module, which would have made it easier to build and probably more efficient with less timber around windows. And there was also additional cost to get it consented because the council hadn't seen the sort of approach or hadn't seen it often. So it was, we required a PS1 to consent it. Bracing was a bit challenging and probably needs some more thoughts. Depends where the stud is in the building, whether the batten's inside or outside, but to get the full perimeter of the bracing element was a little bit challenging. So we ended up having the bracing element between the batten and the stud. But there's probably better ways of doing that, I think, that would make it a lot simpler. And that was partly the problem, was the balloon framing was by design, there wasn't a horizontal batten at the mid-floor level, so there was no way to fix the bracing element. And there was a significant attention to detail, which is probably what you'd hope always happens, but maybe wasn't quite what always happens.
So just some of the takeaway points from this. The framing system was a key element in helping us to achieve good thermal comfort without any need for active heating or cooling. And obviously that helped us achieve our net zero energy goal. There's a small additional cost to doing what we did with the framing and the insulating, but it gave significant gains to the house. Like, we really got the performance to achieve what we wanted it to achieve. The construction thermal resistances for the walls and roof were only about 50% above building code. So it wasn't a major jump from building code. It was a little bit more. There wasn't a significant difference. But the performance obviously was quite a significant difference. But that was also achieved through careful design, you know, thought around the detailing and how the insulation was installed, and then also the construction of that. The framing system was an important part of the design, but you know, the design needs to be thought about holistically for it to work really well. And you know, as we mentioned with the pre-nail company, I think there's a little bit of upskilling of the building industry. And it's probably not just the pre-nail company, it's also from the architectural side of things, you know, the design and build stages. There's a little bit of upskilling, a little bit of experience needed in both places on how to reduce the amount of timber in the walls. An acceptable solution or something similar would reduce the compliance and design costs. As we noted, we had to pay for a structural engineer to do that. And then obviously because we've got no heating load in the winter, we don't have a peak electricity consumption in the winter like most houses do. So that's it. Are there any questions? There was quite a lot detailed in 15 minutes there. It's a bit of a rush.
Thanks very much, Joe and Shay. That's super inspirational. I love your house. And I love also the fact that you put so much of this information out there for everybody to give them the details as well. It's super generous of you to do that and to share all of this. So thank you very much for that.
Yeah, I've put the website address up there just so that if anyone wanted to look at those details again, we went through a bit of a process of finding the right wall construction, and it details that on the website. So you're welcome to have a read through that. Yeah,
that's perfect. There are a couple of questions that have come through, so I'll just read out the first one of those, which is it's from Peter Allenshaw. I'm pretty sure is an architect. Fantastic work, Shay and Joe. Inspirational, he says, but wanted to clarify, when you're talking about net zero, are you talking about energy in use and not embodied carbon or energy? And is that a valid approach as our grid rapidly becomes decarbonised? Operational carbon emissions become relatively insignificant compared to that embodied carbon, embodied energy.
Yeah, that's right. So it was only looking at operational. So our house was built about 10 years ago. There was some information about embodied carbon back then, but it's not as detailed as there is available now. Obviously, that's something that needs to be thought about with new builds coming through, but we didn't look at it in detail back then. It was purely based on operational energy.
Okay, that's great. Thanks for that, Joe. We also had a couple of questions, which I see you guys are so good at multitasking. You've been answering your questions as you've gone through this. But there was a question about the insulation product that you use, and I'm presuming, well, maybe you could comment on that. It's probably much more about the installation of it, and you guys, I know, are very careful about doing that.
Yeah, I think there's a lot of good insulation products around on the market these days. I don't think you'd specifically have to choose the product that we chose. But yeah, like Bernie said, it is to do with the installation. So we made sure that it was all friction fit. There was no gaps, there was no compacted areas. And then where we didn't feel like it would sit very well friction fit, like where we were installing in the roof, we strapped it and we stapled it in place so that it didn't move.
And Ken Mercer's just asked, is it also anti-slump if it gets wet?
Yeah, that's a good question. Probably not.
Yeah, I don't know the answer to
Yeah.
that. And I answered this other question, but Joe's probably got a better answer than me. So the question was, would you use sheathing as bracing next time on outside of the framing with battens on the inside?
Yeah, I guess the reason for our batten placing was to do with the cladding. So
yeah,
I think there's some challenges around, like if you have vertical or horizontal cladding and how you need to have the batten placement. Yeah,
I think we also would need to think about how we did the bracing in the context of that, because I think external sheathing potentially could do the bracing, but there's some questions around that thick build up, whether there's interstitial condensation, and Joe and our scientists here would be able to answer that better than me.
That might be something that comes up in Jason's presentation, perhaps.
No, we won't be talking about
okay.
that. I mean, I might mention it just like you just did. It's a concern.
Yeah.
And, but
it's another topic, I think, that probably needs.
Yeah, it's a full seminar, not a 2-minute throwaway in the middle of a 15-minute presentation.
Yeah. Well, great. I'm just checking the questions there to see if there are any last-minute questions coming through. One of the things I was really interested in actually was your analysis of the cost, because as ever with some of these systems, there's the potential to, I wouldn't say necessarily reduce costs, but there's a trade-off, isn't there? So you might be able to save some money on things like insulation install, if you do away with all those tricky parts that make the labour more intensive on that. Do you want to just maybe just quickly go over whether you think there's a sweet point in there?
Well, yeah, I mean, I suppose our analysis, we looked at lots of options, and this solution actually came out of documentation we got from the UK. So it's by no means new and unique, but we did some calculations alongside Joe's modelling to look at what we thought was, we were getting more timber, and we had cost rates for timber, we had installation rates for timber by the metre, and we did some calculations on that basis. And we concluded that this was the cheapest way to get the R value that we wanted. Because there was less timber and less labour, we obviously have to pay for 2 layers of insulation, so there's more cost there. And in our case, we paid for structural engineers and architects, and there was additional cost probably for the pre-enal as well, because it was a bit weird. So I think we did the best to get the best price we could. But I think at scale, there's reason to believe that this could be comparable in cost to the current approach, or possibly slightly more or slightly less. But given the benefits and the fact that we didn't have to pay $30,000 for a central heating system, there's quite a, the comfort level is of the level of having a central heating system, but without having to buy one or maintain one or run one. So I think holistically speaking, it's a cost saving.
Yeah, that's great. Great answer, because we've got to look at this holistically. I think that's really good. Okay, there's 2 more questions we're going to take, and then I'm going to use Bree's question as a bit of a segue into the next one. So did you have an internal airtight layer?
No, we didn't. We did think about it, but at the time it was quite new to the market.
Yeah, although that being said, the jib is airtight if you seal it, pretty much. So it is quite airtight. If you turn the extraction fan on in the bathroom, you can feel the air coming in through the garage door. So without using an Intello membrane, we achieved quite good air tightness, but we wouldn't certainly expect it to be anywhere near Passive House.
Need to get that garage door fixed, obviously.
Okay, thanks for that. And then we've got a question about what R values were used in the roof space. Was it a double layered system running perpendicular to each other?
Yeah, again, so it was a double layer system. So we had, so structurally you wouldn't need that much timber in your roof normally, but we do have an extra layer. And again, that's about 50% more than building code for the total construction resistance. So there is about 50% more insulation in there, or a little bit more than that.
Great. Okay, I'm going to squeeze in one quick question here, which is from Inling, saying, would using 140 by 45 framing allow you to achieve the same R value, do you think?
No, not with a standard framing approach, I don't think. Is that right?
If you just had a standard stud.
Yeah.
Yeah, I don't think you'd get the same kind of performance out of it that you would do out of the system that we've used.
Yeah.
Although I know someone in Wanaka who's done 140 framing plus a 45mm batten, and they have very little heating in the winter down there. So. Okay,
that's great. Hey, thank you both very much for that. I see there are a couple more questions popping in, so thank you for your questions. We will get to them, but not as part of this presentation, but we'll try and follow up with those in the chat afterwards. And maybe Shay and Joe, you can maybe have a go at answering some of those as well. I'm just going to quickly segue into the next speaker because Bree has asked here, I'm curious to hear facilitator thoughts, I guess that's me maybe, around whether the proposed building for climate change proposals will help take into account these framing issues. And I don't want to say anything out of turn because MB is in the room, in the house here, listening. But what I would say is that, well, firstly, we're really enormously pleased, I think, most of us, with those building for climate change proposals, and hopefully everybody's submitted on that. And yes, as I understand it, the outcomes of today's workshop and some of the other work that's being done will be included in the thinking to inform those building for climate change proposals and the review of the building code that's coming up. So the team at MB, I've got a lot of I guess, optimism that they're working really hard on all of these sort of issues behind the scenes, or maybe not even behind the scenes, quite in front of the scenes. Anyway, that's my segue into our next speaker, who is Glenn Murdoch, and he is an architectural designer based in Christchurch who's been at the tip of the spear of sustainable buildings since the mid-2000s. I've known him since around that time. I've got beard envy now because, as you'll see soon when he comes on the screen, he looks like a philosopher. And he works from a pretty simple philosophical base that every New Zealander deserves to live, work, play, or learn in a building that promotes their health. And that's a pretty good philosophical base as far as I'm concerned. So I will pass over to you, Glenn, to take us through some of your proposed solutions. Thank you.
Great, thanks, Bernie. Hi, everybody. Welcome along. It's great to see you all, or be able to chat with you all. So what I want to do is just offer some of the solutions that we've come up with over the last 15 years or so to address some of these problems. And Joe and Shay have touched on quite a lot of them, but I guess what I'm going to talk about is some additional improvements that we've made on some of that sort of pioneering work they did 10 years ago. I'll switch to here. So what I want to talk about is solutions that are regularly being consented and built. They're not off the wall. They're very simple solutions. They all work within the existing regulatory framework. So there's very, very limited specific engineering required to implement these solutions. It's stuff that builders already know how to do. There's not revolutionary products or building methodologies there that they have to learn. There's no interruption to a typical build process. There's no need for subcontractors particularly to visit site when they wouldn't normally. And it provides some opportunities for significantly improving our building performance beyond the reductions in framing proportion. And I'm going to talk quickly there about some of the questions that came up in the last presentation. So I'm going to talk about four solutions that we can really easily implement. So the first one is just get rid of the damn dwangs. So if we think about the primary purpose of dwangs, they're primarily a structural element designed to provide lateral support to studs. And if we look at 3604, 3604 offers a couple of methods of providing this lateral support. So part B there is using dwangs. But there's this other option here, using exterior wall claddings complying with E2. And as the question just came up earlier, part of a wall cladding system that complies with E2 is a rigid air barrier affixed to the outside of the framing.
Glenn, sorry, can I just interrupt to say, are you sharing your screen with us?
Perhaps
or
not.
Could you please?
Oh,
We'd love to see your screen.
Wouldn't it? Let me just go back a couple of slides to make sure I'm in the
Not
right
just
place.
your beard, your screen would be good too.
Sorry. Remind me where to share my screen is. There we go. How's that?
Yeah, that's looking very good. Thank you.
Okay, great. Okay, so there's the framework I've talked about. Okay, so the first solution is get rid of the dwangs. You want to see that?
Love that,
Okay.
Rocky.
So 3604 offers these two solutions. So part B there using dwangs, or part A using wall claddings complying with E2. And a part of that wall cladding solution can be some sort of rigid sheathing on the exterior of the building. And this can, we'll get to a point soon where you'll see that this provides some other significant benefits, putting a rigid sheathing on the outside of the building, primarily around bracing. So one of the other reasons that we tend to put dwangs in exterior walls particularly is for cladding fixings. And nowadays there's a lot of claddings that require quite a lot of timber to fix them to, and particularly, as Vernie talked about in his introductory document, the vertical shiplap weatherboard scenario requiring fixings at 480mm centres. So how do we solve that problem? Well, that's actually pretty simple. We can just use some structural cavity battens. And again, we don't have to design or invent this stuff. It's straight out of the book. Just put on some structural cavity battens at 480mm centres, and then my need for dwangs has disappeared. It's very simple. So the second thing I want to talk about is detailing junctions properly. And Shay and Joe talked really well about this a bit. And I want to just, so again, take what I've learned and advance their thinking a little bit further. So if we just look at this, the typical junctions, and we understand why these junctions don't work. So here's a typical external wall junction that we've been using for a long time now, for a number of years. And what we can see, can you see a laser pointer there now? Does that work? Can you see that my red laser pointer? I'll assume so.
Yeah, we can see it. Thanks.
Okay, great.
Sorry.
Okay. So here's my primary framing layer, and in this particular instance, I've got 140mm framing, but that's not critical. It can be 90mm framing. Here's my rigid sheathing on the outside, and it's straight away in this corner I've gotten rid of that typical stud that would be sitting here in order to fix internal linings to. And what I've done to be able to remove that stud is, like Shay and Joe have just been talking about, use some horizontal service cavity battens on the inside of my framing. So then what this also gives me the opportunity to do is to add in a vapor control layer here, which is indicated by the red line. And I'd argue that if we're going to improve the performance of our wall by reducing the amount of framing we put in to increase the amount of insulation, we also need to make sure that insulation can perform as well as it's possible for it to do. And a vapor control method, a layer, is the simplest way to do that. So then again, like Joe and Shay talked about, I've got some additional insulation in that service cavity. So bringing my horizontal battens to the inside gives me some other advantages. Now any blocking that I have to put in for fittings and fixtures, Vernie had those great examples of blocking for the stairway, for example. All of that can now happen in my 45mm service cavity, in this cavity here. So that means that my primary insulation layer remains untouched. So this detail here gives me a negative psi value, which is a pretty good result. If this number here is below 0, then I've got some wins. So then, now that I've removed this stud, what am I going to do to fix my internal lining? Well, you might be able to see there's that cheeky wee angle in the corner, which is just very simply a steel corner angle. Off the shelf, nail it on, and now I've got some fixing in the corners for my internal linings, whatever they might be. And I don't need any vertical timber there. So we are typically putting these horizontal battens in at 600mm centres to suit the fixings required for my internal lining systems, whatever they might be. And this angle will easily span across those. So there's an external corner. So if we look at internal corners, now internal corners are much more difficult. I need a bunch more framing in my internal corner. I can't get away from it. And this is the best I've been able to do for my internal corner thus far. So the main difference I've done is turn this stud on its side to allow insulation to continue into here. And then I've just moved this stud away a little bit to allow this space here to be more easily insulated. And that's mostly actually to get that cavity batten over far enough for my cladding fixing. I have to have this stud to fix my cladding to. So this internal corner gives me a psi value of plus 0.06. So that's a greater positive than the negative for my internal corner. So what we can see from this is that there's a design problem here. The more internal corners I have, the worse my building's going to get. This is a great combination of a geometric and a material thermal bridge in this internal corner. So if I can design out as many internal corners as possible, then I'm going to be making my building better straight away. So if we carry on to these typical junctions, so here's my internal external wall junction. So again, because I've used the cavity battens on the inside, I can run my moisture control layer and my cavity batten insulation layer straight through. Then I do need to make sure I've got a stud in this location here, and I can now just screw my internal wall frame straight through into that stud. If this wall is a bracing element, then just up at top plate level, I can connect those bracing elements together. So it's very simple. And this gives me a psi value of 0. I've got no additional heat loss through that. And then if we move to the mid-floor junction, oh, sorry, and there you can see again, I've got my steel angles there to fix my internal linings to. Very simple. So if we move to a mid-floor junction, so once again, because I've got my 45mm cavity on the inside of my framing, I can now put a ribbon board in there, screw that to my wall framing, and sit my joists on top of that ribbon board with blocking in between to prevent rollover. So once again, I've got a continuous line of moisture control, a continuous line of insulation. And my thermal bridge value here isn't too bad. So the next thing I want to talk about is just thinking better about the openings. And Vernie's talked a bit about this, and Guy as well, about just thinking a little bit differently about the way we detail the openings. So if we look at this typical wall scenario, so a 3.6 by 2.4 meter wall with an opening in it, and we can see that the framing content on this particular one is over 50%, so pretty high. And this is assuming studs at 600 centers, dwangs at 480 for some vertical cladding fixing, and the typical jack studs and trimmer studs around the window opening. So if I get rid of my dwangs and just think differently about how I can do this, here we go, sorry, there, that's what I want. So now I've reduced that only down to 48%. So it's not a massive reduction, but that's because there's this big window in there. So we can clearly see that there's a whole bunch less timber in this detail. The second change I've made is just made my window very slightly narrower. And Vernie talked about this, very small design changes. So that allows me to remove a stud. Then if I think about this structurally again, another benefit of using plywood sheathing on the outside of the building, and I say plywood sheathing actually for a good reason, I'd use a timber-based sheathing rather than a fibre cement-based sheathing because of the embodied carbon in it. So putting my plywood on the outside straight out of the book allows me to put some simple lintel hold-down fixings in there. So on the top ones here, straight out of the book, so long as I don't exceed a 7.5 kilonewton uplift requirement. And that covers most of the scenarios in my experience. We really have to start pushing the building design to require a higher uplift connection than this. Now this detail from the EcoPly manual specifically excludes it being used here. So this one does require some engineering input. And every time I've talked to our structural engineer and they've said, that's no problem. Put some plywood on it, put plenty of nails in it, that's no problem. You've got no problem at all. So there's a whole bunch of benefits of putting this plywood layer on the outside of the building. And then the last thing I want to talk about is the design fraternity taking responsibility more for what we are doing. And I'm arguing, and we do this as a matter of course now in our practice, and we're modeling the framing in our buildings. So most of us now are using one of these two BIM packages, ArchiCAD or Revit. And within both of those packages, there's off-the-shelf, very smart and automated framing modeling solutions. And what I've learned is that once I start to model the framing within my BIM model, then I can very quickly see where problems occur, and at the design, as a part of the design process, I can resolve those problems. So just one thing to note here on this particular building, this hasn't been balloon framed. I can see there's a top and a bottom plate through here. And if I flick back to my to my mid-floor junction, this is shown as balloon framed, but I can, if I need to, put some plates in here if there's some logistical challenges around using balloon framing. So I think from an industry side, from a design perspective, we need to be smarter, eh? We just need to think more carefully about this and take responsibility for what we're doing. And then we need to push the boundaries, like Shay and Joe talked about, eh? Pushing the frame and truss manufacturing industry to not just do what's ordinary or what's typical, but to start to step it up for them. And then in terms of statute and regulation, this H1 review, building code review, hopefully that's going to come to the party. And I'd be really disappointed if these conversations don't make it into the reviews there. And then one of the questions that's always in my mind is about 3604 and to what extent it's over-engineered. If you talk to structural engineers, they'll typically say that there's a fair bit of redundancy in there. And I just wonder how much of that redundancy can be removed from 3604, which may lead on to having just less framing as a standard course. And maybe this leads to a new 3604 as a part of this building code review, which would be great, having some of these really simple solutions as a standard detail in 3604. That's me. I'm welcome questions. This is an image of one of our projects in Christchurch, which was New Zealand's first certified Passive House Plus, which used every single one of those details that I've just shown. So, welcome questions.
Thanks very much, Glenn. That was awesome and full of loads of really good detail in there, which is superb, just exactly what we need. I can't see yet any questions coming through. You must have stunned them with those fantastic images of Bruce Lee and Rocky and the model at the end. But I definitely have a question for you, which is around, it's probably pretty unusual, I would say, for a designer to be modeling the framing. So I'm just wondering from your experience in doing that, does your software then talk at all to the framing software at the frame and truss factory? Are you using frame and truss? How does that operate?
Yeah, it's a work in progress. So the answer is yes, but. So it has the potential to, but it's a work in progress, and there's maybe some development by the software folks to work on that.
Sure, great, okay.
If you're thinking about just a simple, it depends on the frame and truss plant. If you're talking about a highly automated one with proprietary software systems, then that's more challenging. If you're talking about a more simple frame and truss plant just using cut-off saws, then that's easy.
Thanks, Glenn. There's a couple of questions that are coming through on the chat, so I just want to highlight a couple of things. One is, when you go to add something to the chat, could you use there should be a drop-down menu which allows you to chat to panelists and attendees. So you need to set it to that so that you're chatting to everybody that's out there. Otherwise, it's just us lovely panelists that get that. And we want all the lovely attendees to get it as well. And then also, if you have a question, it's much better for us if you can put that in the Q&A rather than the chat, so that we don't have to scroll through too much of that chat. But anyway, let me go to a couple of these questions here. Gleb Speransky from Brands, he's not a question, but he's saying that NZS 3604 revision is getting underway next month. So there you go. It's very good. And then we've got a question from Jason Quinn of how much longer in terms of time does it take to model the framing?
Yeah, sure. So the add-on to ArchiCAD that we are using is fairly automated. So the setup process at the start took a bit of time. And that image that I showed, that was a pretty complicated one in a ECH wind zone with balloon framing and a whole bunch of stuff. So that one was complicated, but a typical two-story house. So that image that I showed of the passive house, that would take me 2/3 of a day, something like that, 6 or 8 hours to model that framing.
Sure. Okay, that's great. Thanks, Glenn. So a couple of other questions coming through in the Q&A now. What software are you using for the psi values of different junctions, from Anthony Hopper?
Yeah, so there's a whole bunch of different options out there. So I use Psi-Therm, and I'm not going to argue that it's the best one to use. It's in terms of its usability, it's not ideal, but there's plenty out there. Flexo, there's plenty of options.
Great, thanks, Glenn. You can tell it's a pretty technical audience because we're getting questions about
exactly.
psi values and so on, but that's very good. It's very good. I think we're up to that challenge. And then a question again from Inling. I believe if RAB is used as structural element, then fixings, the nails and screws, need to be stainless. Is that correct in your experience?
I'd have to go back and check. I think that depends on the product that you use.
Yeah, I guess it would be, but yeah. Inling, we'll have a look into that and then try and get back to you with a definitive answer. Maybe some other people at Brands could also answer that question for us. And we've got a question here from someone who's remaining anonymous. Has the Arche frame info been sent through to the frame manufacturers to ensure this is what then happens on site? So I guess it's a question about that consistency.
Yeah, exactly. Yeah, so like I said, the Arche frame data, we haven't been able to get that into the frame and truss plants yet. So just as a matter of course, we're just doing our usual on-site observation work to make sure that nothing stupid is happening on site. Like I said, just as a part of, I mean, everyone's the same. We've got our typical builders that we work with that understand this stuff and know what they're doing. And we work with those usual folks as much as we can so we can be confident that what's going on site is going to be what we want.
Great, thanks, Glenn, very much for that. Anybody else? Oh, we've got another question here. Do you need any additional cavity battens to install a vertical cladding over CLD battens?
You'll need, just typically you might need some extra stuff around windows and things, but it's just pretty standard stuff. It's nothing special.
Great, okay, thanks, Glenn. That's really excellent. If you've got any more questions for Glenn, please just fire them through. And again, Glenn may be able to answer those online as we go through this, but we'll launch ahead. And yeah, just really, that was awesome. Thank you, Glenn, very much for your input there. So now we're going to move on to talking to the famous or infamous Jason Quinn, who you've already seen pop up to answer a couple of things as we're going through this. Now, I'm very pleased to report he is an ex-NASA international professional engineer, so I don't think I've ever moderated a session where we've had an ex-NASA person on the team, so that's very good. Now working as a passive house designer, certifier, and building scientist. And Jason's work, like probably much of ours, is driven by concerns about the future we're creating for our children. And his main commitment to passive house concept springs from the potential to significantly reduce carbon emissions and its rigorous measurability. So very keen on that science-based approach and measured. And yeah, welcome, Jason, and look forward to hearing from you.
Thank you. Appreciate that. Let me see if I can successfully share my screen this time. And then we'll put this on display, right? Slideshow. All right, so can you see the slides all right?
We can, thank you. That's working perfectly.
Sweet, good. All right, so the I wanted to go through a few things, and luckily Glenn, took care of a lot of the prep for me, so that's wonderful. I really appreciate that, Glenn. So I did want to point out that he ended with, it's nothing special, but his nothing special wall systems, like an R4 something wall system, real R4, like accounting for all the thermal bridging and installation install and all that stuff. Whereas we saw a guy talk earlier about an R1.3 wall assembly. So it's nothing special, but the results aren't. And I believe Joe's assembly and Shay's assembly was probably something around R3.8 as well. I actually didn't catch that number. So I wanted to talk about the high performance construction details project, which I've been working on for the last few months, along with my team here. And this project is a FINS, Passive House Institute New Zealand, and Brands project that's funded in part by the Building Research Levy. And this project, the whole idea is, as a passive house certifier here in New Zealand, I get to see a lot of very high performance projects. So I see Glenn's projects, I see a lot of other projects at Archetype out of Dunedin, see projects by E-House out of Auckland, and by Daryl Singh Architects and such. So I see a lot of high performance building projects. And the idea is we have all these really good ideas and designs coming through, and to try to pull out common details for those projects that are actually being built in New Zealand and actually consented. My working title for this project originally was accepted solutions rather than acceptable solutions, to try to play on that words, but it got kicked out to the curb by brands, and we have this nice title instead. So the idea is to pull together a library of details for projects that are actually being built and consented in New Zealand, and then compare those to current practice in New Zealand. The big focus was on timber framing, because we knew that the Building for Climate Change proposal was coming through from MB. So we did focus on that, but other constructions included. And then the main focus of the project was on thermal performance, but brands came to the party with some really good research. So we'll also have cost and carbon footprint for all those constructions. So you'll not only have a wall element that looks at the performance of that wall element as you do something clever like Glenn showed or Joe showed, but also the reduction or increase in embodied carbon in that wall due to it being thicker or having additional or more or less timber, that kind of thing. I almost always look at passive house projects because that's most of our work in our firm. And in passive house projects, the walls are almost always the weakest construction that's built on site. I mean, obviously windows tend to be lower performance than walls in passive house, but definitely the walls are where the weak is. So when we've got a project that's trying to meet the passive house standard, trying to get down to a very, very low energy use, down to where probably Joe's building sits, the zero energy building sits, then we oftentimes have to upspec the wall constructions. And commonly in Auckland, you might use like a 90 mil stud with a 45 mil batten. Down in the rest of the country, you might use a 145 with a 140 stud with a 45 mil batten, such as Glenn showed. For some projects down in Christchurch that have a lot of glass, we might use a 190 stud, and we've even gone up to a 220 stud in some projects, which is quite a thick wall assembly. All right, so what's the high performance construction details project gonna look like? So when it's done, it'll have kind of two categories of results. The first category is what we're calling elements, and that's when we're looking at a kind of what I call a 1D assembly. We're looking at a wall. So this is the wall. This is the wall assembly Glenn talked about right here, right? It's a vertical 140 stud with an insulation bat and an air vapor control layer, and then horizontal timber battens with interior insulation, and then gypsum board. So the point, so what's going to be in here is we plot graphs versus timber fraction for those wall assemblies, because as designers, we're going to end up with varying timber fractions and varying walls depending on what kind of structural loads we need to deal with. So if you think about a conventional practice wall that varies somewhere around R2 down to 1.3, depending how much timber you have in that wall assembly, whereas we look at a 140 by 45 stud wall, such as Glenn showed, you can get down to about 8% wall timber in that wall if you have no dwangs and you account for the timber around the windows and such in your thermal bridge calculations. So you can get to something like an R4 to R5 wall with a 140 frame and a 45 stud. A 140 stud and a 45 mil service cavity. And then if you want to, oftentimes we'll try to upspec projects, we'll have to get to something up like an R6 wall. So what's in here now is from performance, and this will all be coming out in the draft later this, well, hopefully the end of this month for review internally, and then out to the public. We'll see when that gets out to the public. But also will be in there, will be cost and carbon for several versions of that wall. So you can see what the approximate dollar per square meter is. So you can compare current practice to these upspec wall assemblies. And also the embodied carbon through construction will be in there. So, all right. Oops, wrong way. Let's go down instead of up. There we go. So in that package, there'll be 7 different wall assemblies. There's actually 18 different elements, but there's 7 walls, ranging from a wall assembly that Glenn just talked about, which has a stud kit layer with a flexible wall underlay. A flexible air vapor control layer, and perhaps a rigid air barrier on the outside, to something we're seeing more of now in passive house. We're seeing more assemblies where people have flipped the wall assembly and put the rigid air barrier on the inside of the stud layer, leaving themselves a flexible wall underlay on the outside. This helps with bracing a bit and does make it for less likely to have problems with air tightness in the building. Another wall assembly using steel battens in the interior service cavity. And this one over to the right here is using an I-joist. So there's several passive houses built with I-joist wall assemblies, which is really reducing the timber fraction. With this wall assembly, you can get down below 8% timber in the walls, which significantly enhances the performance. And then we'll look at some other assemblies which we won't talk about here, like ICFs or straw bale walls as well. But it'd be good to have some cost and carbons for those constructions. All right. So then this is an element. So we talked about an element before. This is now a junction. So there'll be 83 of these junctions in the document, and this is a current practice one. And in those, we have calculated the additional heat loss at this corner due to the presence of this additional timber and actually lack of insulation in this corner. And that comes out with a psi value, which is the additional heat loss of that corner. And also we look at interior surface temperatures to look at mold index in those assemblies. So this is kind of the two bits, right? You get elements and then junctions. And then we go through and look at what's going on. So none of these ideas in this package are new ideas. If you look at SR 246, which is a report from Brands back in 2011, you know, they actually have pictures that look very much like Glenn's pictures, with only a 90 mil stud, of course, but they've got the steel angles to remove the additional studs at the interior wall to exterior wall junction. They've got some steel angles to remove the studs in the corner, so you can use a 2-stud corner. One catch which wasn't mentioned in SR 246, but Glenn luckily mentioned it, was that when you take out the dwangs or nogs in the wall assemblies, you really have to be careful about structural cavity battens in the cladding assemblies. I've had several projects that had problems during consent stage and construction stage because they switched cladding assemblies during construction. The person who bought the building wanted a different cladding, which was great, except now they had to put structural cavity battens on the building, which changed everything. So, so that's just something to watch out for. Now, when we look at this document, I've stuck in the most scary picture I probably could, but what this is a external corner in a wall assembly. So if we look at the leftmost picture of this, this is a current practice 90 mil stud wall with gypsum board on the inside, and a typical stud corner junction with some blocking and air in it. And for that assembly, not only is there additional heat loss, but there's also lower surface temperature in the corner. So if you look at the surface temperature of that gypsum board in that corner, assuming there's no wind washing through this insulation and the exterior flexible wall underlay works well, you still get a FRSI that's low enough that south of Auckland, I would not allow that in a pass house because I'd be worried about mold, even with an interior moisture, with an interior ventilation system. I'm sorry, mechanical ventilation system. So that's there. Now, if you take that same assembly and you switch to a 2-stud corner, like Glenn showed, but again, just a standard 90 mil stud with interior gypsum board, now you need to use a metal angle to fix your gypsum board in the corner, which means you may have bracing problems, but you can increase surface temperature as well as reduce the heat transfer. Now, we can talk about psi values, but unless you work with psi values all the time, the numbers are completely useless to you. I mean, other than it gets better, right? That doesn't help at all. So what I did is I looked at a uninsulated slab edge. So if you think about it, a normal 90 mil, a normal current practice building in Auckland on a concrete slab, it has additional heat loss out that slab edge. And it turns out that if you switch from this corner, which is kind of current practice, to a 2-stud corner on a 90 mil framing, the reduction in heat loss per height of wall, that height of that exterior corner, is about a quarter of a similar length of uninsulated slab edge. So you know, when Brands talks about insulated slab edges are really a problem, we need to try to fix them, and they are, by the way. When we can change small elements in a wall and get 25% of the benefit of having slab edge insulation on a building by taking stuff out of the building. So you've removed materials and you've saved increased performance at the same time. All right. Another junction we look at that Glenn looked at luckily, and we've looked at in this study as well, is the external wall to internal wall junction. So if you look at a current practice junction over here on the top, it looks at the heat transfers of that junction with blocking and air in the corner. So this is where the interior wall runs in, the standard current practice. You end up with a psi value for that. And the surface temperature of this interior wall actually meets the mold index criteria for the whole country. But the performance of this is quite poor because of this blocking and effectively no insulation between the blocking, timber blocking, versus an assembly that looks just like what Glenn showed, but in this case for just a 90 mil stud wall. And the difference in performance here is about half the similar length of an uninsulated slab edge. So again, if you think about, can I afford to buy slab edge insulation in Auckland? Is it worth it? Just changing the way the internal walls are framed to the external walls can be 50% of the benefit of putting slab edge insulation in the building. All right. And timber fraction of the wall. So Guy early on spoke about timber fractions in the wall, and it's really important as an industry we develop a kind of a language around this. So there's effectively two kinds of timbers in a wall. There's timber that's, you know, kind of a, what we call a uniform or repeating thermal bridge, where you've got normal studs kind of on centers, or dwangs or nogs on centers, that you take into account when you calculate the insulation value. So, and then there's also additional timber that's directly around the window, or directly on top plate and bottom plate, or in a corner. And I'm arguing that as we go forward with 3604 and H1, that we break those into two piles. So rather than talking about a wall that has 32% timber fraction in it, or 50% timber fraction in it, we take into account the regularly repeating timber, including any additional timber if we put additional timber for jack studs and king studs underneath walls, or cripple studs under the wall, and the pile that's used at the junctions. And the reason I'd like to break those out differently is because when you're trying to calculate the overall performance of this wall, the most efficient way to do it, and the way it's used, the way it's done internationally, is you account for the timber in the overall field of the wall as a fraction of timber mixed with the insulation. And when you look at the timber in the header and the timber in around the windows, you need to account for that separately, because if you roll that fraction into the fraction of the wall, it just disguises what's going on at the junctions. So when this publication's used, and we're looking at this junction here, and we have a psi value, a thermal heat loss at that junction, this heat loss here accounts for the timber in the corner. So when Guy summed up the timber fraction of his walls, he had to keep that separate so that he could account for the heat loss of that corner separately from the heat loss in the main in the middle of the wall. Thank you. All right. Excuse me. Sorry about that. Okay. And then that's about it. So when we're looking at timber and walls, I want to remind us that we not only do simple buildings, like the ones that Beacon Pathway looked at, which are kind of standard construction, we also do very complicated buildings in New Zealand, where you have pitched roofs, meaning flat roofs, and you have buildings where they have unconditioned basements with a conditioned section of basement poking down into it, or wing walls poking out. And all of those additional features can't be addressed by just going ahead and trying to raise a timber fraction in the wall. Like, let's say we decide, well, instead of assuming we're going to have 15% timber in the wall, we're going to assume we're going to have 40%. And we need to account for that in our R values. I want us to step up in looking at this into breaking our timber into two pieces, and to have a piece that looks at the junctions themselves as well as the walls. All right. And that's where I wanted to stop. Thank you.
Great. Hey, thank you very much, Jason. That was really good. And I'm so looking forward to that list of 101 details that are coming out soon. That's going to help give us a whole load of really useful exemplars, and particularly good, I think, to go into all of the carbon calculations and the cost calculations. And it's a pretty complicated process. So well done for undertaking that fine work.
Yeah, I'll be looking at, I'm interested in hearing the carbon and cost calculations as well, because I can't do those. So.
Yeah, I believe Brands is hard at work on those. Yep. So that's excellent. And there's a really good team at Brands working on that too. Okay, so we have got some questions through from you. And just once again, for all of you attendees out there, if you want to ask a question, use that Q&A button at the bottom, or you can raise your hand and we can try and get your audio live. But it seems to be working pretty well actually with written questions. So first of all, we're going to go to a question from Peter Allenshaw again. And he's really talking about the fact that you said there'd be more embodied carbon with more timber framing, but he's asking, well, if it's timber framing, surely that's carbon negative. So the more timber, the better. Is that not right?
Yeah, spoken wrong. I said it the wrong way around. Thank you. You're right. So there would be more embodied carbon with more insulation, and it does somewhat define how they actually calculate the embodied carbon. So there's two ways they calculate it. One way, they take into account the benefit of the carbon stored in the timber, the biogenic carbon is what they call it, and one way they kind of ignore it. So depending on which number you look at, it could be worse. But in reality, I agree. The more timber in the walls, for storing carbon perspective, that's better.
Great. Okay. Thanks, Jason. We've got, it's more a comment than a question from Arama Black, who might well be from Jib, because we've got a few people from Jib listening in. Just to clarify, they're saying Jib fix angle for the corner junction can be used to fasten off a bracing element. So that's just a clarification about that. Again, that kind of excellent Jib fix system. Then we're going to go to a question from Bree again, saying, is anyone familiar with the Eco Panel system? I'm not exactly sure which version of that there is. We've got Dan Saunders going to be talking a little bit later about his Eco Panel system, so that might be the one you're talking about.
Yeah, so Eco Panel is a company in Christchurch that builds wall assemblies that are sort of like this. So the most common assembly used in passive houses in New Zealand is the system that Glenn showed you earlier, the 140 stud with a 45mm surface cavity batten and an air control there. So Eco Panel prefabs that with insulation and then ships it around. And I think Glenn's company did that a while back as well.
Okay,
Yeah,
thanks,
right.
Jason. We'll get. Oh, yeah. Sorry. Go ahead.
Yeah, sorry. Yeah, that's right. We had to play with that as well. I just answered Bree's question there as well. I mean, whatever method you use to create or to build your wall or your roof framing system, the same problems can be either introduced or solved. Doesn't matter where it's built. You can solve or not the problems.
Yeah.
Great, thanks, Glenn. That's really good, and thanks for answering the question there. We've got a question again from Anthony Hopper here, a bit more of a technical one here. Where did the FRSI factor of 0.25 for passive come from? What's the science behind it, and why do we use 0.13 for U value calculations?
Yeah, so the 0.25 comes out of DIN 4867, which is a German standard. It might be anyways, I may have got to those digits turned around, sorry. If you want, Anthony, just email me and I'll send you the correct DIN. Anyways, it's a German standard. And so the 0.25 is supposed to account for things like curtains. And, you know, you might have a couch pushed up against a wall. It's interesting because the Germans do this internal surface temperature calculation, and it only accounts for the mold on the surface of the gypsum plasterboard, whatever brand it is. And so it doesn't account for moisture problems inside the wall itself. So it depends on that wall as being a flow-through assembly or having other problems for other ways to deal with interstitial. But the 0.25 is supposed to account for that lower loss. Interestingly, in that same standard, there's actually a number you use for inside kitchen cupboards on walls that face the North Pole for them. Well, it'd be the South Pole for us. So your south-facing cabinets you brought up earlier, Ernie, would have a higher number than that 0.25 in them because they use a different number. But yeah, so it's just been adopted by Passive Institute as the standard to use for all their FRSI calculations. And yeah, I guess that's it.
Great, thanks, Jason. Yeah, it gets complicated pretty quickly when you start delving into those values and different international standards. And
yeah, and they're all experience. I mean, they take into account temperature and they look at it, but it is also experience-based. So there's different levels of FSR requirements per climate. And the ones we're using right now, the ones I had in the presentation, the ones I'm promoting are promoted by Passive Institute out of Germany. So they're very conservative. And actually the next version that they're going to come out with of PHB they're going to come out with is actually going to reduce the requirements slightly. And as they're getting more and more confident to reduce their margin, as it were.
We've got a follow-up question to that actually from Anthony Hopper again, which is, does that make it 100% relevant for our climate? So it's that kind of internationalization of those sort of standards.
Yeah, so it's actually climate specific. So for Auckland, the FRSI requirement is 0.55, whereas for most of the rest of the country, it's 0.65. And for Queenstown and the Highlands and Otago and such, it's 0.7. So again, it's they've studied that across the climate zones. So, and they agree it's conservative. So they would like to lower it as much as they can as they go forward with research. And that'd be something brands could and us could step up to with doing more applications research and then trying to lower the number. Because it does mean that a lot of our conventional joinery systems, even the higher performance joinery systems that are manufactured in New Zealand, have real problems with the FRSI requirement. And oftentimes we'll import systems from Europe and then make them easier to build for New Zealanders. And in doing so, we'll significantly lower the thermal performance. So we'll have a system that was, let's say, imported from Italy that met the standard, and now we've modified it for New Zealand. It now does not meet that standard. And it's done to try to make the building systems easier for us to build. So.
Okay, thanks, Jason. Yeah, that's a really important point to raise there. Okay, look, thank you very much for that presentation, full of really good, very robust scientific facts. And as I say, really looking forward to the research being completed that you're undertaking and seeing results of those. That'll help inform this process, I think, really hugely. Okay, we're going to move on now to the second to last set of presentations. Now, I'm aware some people have had to leave, but we've actually lost about 2 people in terms of attendees. So all of you guys are doing very well, hanging on in there, and I think it's really good because we've got a couple of really good presentations coming up now as well. The first one, who I shall introduce now, is it's from the Super Homes contingent, and so out of Super Homes we've got the wonderful Mr. Bob Burnett, who has received recently the Sustainability Superstar Award from the Sustainable Business Network, and that's just about all you need to know about Bob. He is a total superstar in this industry in terms of setting up with a bunch of other passionate people the Super Homes movement. And he's going to present alongside Damien McGill, who was the first engineer to join the Super Home movement and first to be appointed to the executive. But he's had a lot of experience both here and in the UK. And then also Dan Saunders as well, from Dan Saunders Construction, who, as I mentioned, also does these great eco-panel, sort of panelized wall systems that I'm sure he'll be able to talk to and answer any questions. So without any further ado, I'll pass over to you amazing Super Homes people who are coming to us from, I believe, Christchurch and Invercargill. So Bob, take it away.
Cool. Thanks, Bernie. Can you hear me okay?
I can hear you. I'm pretty sure everybody else can too. That's all good. We're getting thumbs up.
Thanks for that intro. I think you're a bit of a superstar yourself, so thanks for the invite to be here, and thanks for all the work that you have done, and Guy and others. It's really interesting to see, probably quite frightening to see some of the results. So I have Damien McGill with me here. So you're getting 2 for 1. And Dan is online as well.
Invercargill.
In Invercargill. So it's really, I think it's really great to have a designer, a builder, and an engineer to have this conversation about walls or super walls. And in a way, I think my presentation, I'll just share my screen now. So my presentation is, I think, maybe doubling up. So some people, some of the good stuff that Joe and Shay and Glenn and Jason have shown, some of the details might be repeated, but I think, you know, it's just good to reinforce it too. So this, is everybody seeing my screen at the moment?
Yep.
It's working okay? Cool. So this house here was really the first super home, and it's been fairly exposed through media, so people know about this. But this project was the first house that we did a number of new things, and first 10-star home, Homestar, and each job we do, we learn something really, and the next one's better. So, you know, this is 5 years ago, so this is really out of date now. And, you know, the project that we did immediately after this, I thought it should be the 11-star home because it was better than the 10-star home, but there's no such thing. So we did things like the jib fix wall system, which if we look at this slide here, here's our, you know, we've already talked about this, but, you know, it just sort of reinforces it. We've got our 3 studs. You actually don't need any studs at the internal junction. So on the right here, we've got the better way of doing it. We also completely got rid of a lot of the dwangs, except for some that were needing to be retained. So the red here obviously shows the extent of the insulation that you can get into the wall. So we went a few steps further with this. So I think this might have been the first house, or one of the first houses in Christchurch. Before it was called Jib Fix, I think it was called Frame Saver or Stud Saver. people have been doing this for a while. In America, it's called the Californian corner, I believe. So just getting rid of the corner studs and also the internal wall junction studs. The rondo type metal angles go in there, which jib-like because it makes it better for fixing the jib. But also help a lot. And apparently the bracing is even better than a normal conventional wall using this system. So we didn't do ear tightness. We were learning about that back 5 years ago. We didn't do an internal services cavity, but that's our go-to method now. And basically, same as what Glenn was and others have already illustrated our details. And that's pretty much what we call the super wall. Structural cavity battens. So really important to reduce the amount of framing that's required for fixing claddings. You're also reducing the penetrations in terms of the weather-tight envelope. Rigid air barriers. So this job here, we did do a rigid air barrier. We went around. That's me there pulling the dwangs in. So we went around and got rid of the dwangs. The next job that we did after that, we just said when we ordered the frames, we said, don't give us dwangs. We didn't want the dwangs. So, you know, back then we were using the James Hardie's fibre cement rigid air barrier. This project, we had to account for all the waste, and the biggest, heaviest waste component was the fibre cement. We had some fibre cement claddings too. So we had to have less than 10 kilograms per square metre of waste and to be a 10-star rated home. So it's really affected doing that, and just thinking about the embodied carbon and also dealing with the waste has really affected the materials that we use in our design, which has been great. So we're now tending to use materials that can be either recycled or composted that don't have to go to waste, which I think is really important, as well as the carbon, because 50% of the waste in the construction comes from in general going to landfill comes from construction. So we're talking about walls, but I think it's really, really important how the wall connects to the floor. And I personally think we should just all be doing 140 framing, and that allows us to get a really good edge insulated detail on our floor. And I think it should be mandatory to have an edge insulated floor, or either that or at least a thermally broken floor in some way. So there's different ways of doing that, and I think that's the important thing. You know, there's a bunch of different ways of doing things, and all many of them perfectly valid ways of doing things. So another thing we did on the right hand side here is this little sketch. We actually insulated between the lintels with our 140 frame. So we used sort of semi-rigid insulation in there. So wherever we could, we fitted insulation. So the super wall really is basically eco panel, but built up on site. So eco panel is a whole wall system. So it's not really a panel. It's, you know, if you've got a 10-metre long wall, you've got a 10-metre long panel coming off the truck, and that saves a lot of time and issues. And prefabricating, again, a good way to reduce waste. So I think it's something that's been talked about a lot in New Zealand, and we hasn't really come to fruition. It's been a promise that hasn't been realised, prefabrication. And there's a lot of advantages that Dan might talk about later. You know, just keeping everything from getting wet on site is a good one too. So let's keep moving. So here's our internal corner. So, you know, some of the images in the wall framing report about the number of studs, it's frightening. You know, you can end up with 4 or 5 studs at corners, and it's really unnecessary. So Damien's just going to talk about.
Hi all. So this is a detail that's going to be in our upcoming Healthy Homes guide, basically summarising all we've just been talking about. What I wanted to use this to do was just quickly talk about bracing. From my point of view, the purpose of a wall is to hold up the roof, and if we don't do that, then all we've got is expensive looking duvets. So what you've got to consider is where your bracing element is. And as soon as you put a cavity in, then you've really got to be your bracing's really got to be your rigid air barrier, or as Jason and others have shown, you can put a bracing layer in between your cavity and your frame. But there's a trade-off here, which people in Canterbury, Kaikoura would understand well. Under earthquake loading, you can get damage to your bracing layer, and if your bracing layer is hidden behind your cladding or behind your lining, it can't be seen, and so you've got no idea the damage that's been caused. So what we've got to do is not go back down the path of, and I'm not saying I have all the solutions here, but what I'm saying was don't go down the path of the leaky building situation and solve one problem by creating another one. So we need to be very careful. And there's been lots of comment about the redundancy in 3604. I disagree. 3604 was built for very simple structures and not for the sort of structures that a lot of our houses are being designed to look like now. It also has a ductility of 3.5, which is quite flexible. And with all your tapes and air tightness barriers, any lateral movement or more than a minimal amount of lateral movement is going to potentially break those tapes. So all this needs to be considered as a whole holistic system, not just as individual bits and pieces. So yeah, that's really what I just want to say. Whenever you're coming up with all these details and all these designs, don't forget the structural implications of bracing and, as Bob says, foundation connections and the things that actually hold the building up. Cool, thanks.
Thanks, Damien. So I think that's really sort of a valuable insight structurally. So in our buildings now, we're doing a detail like this, where we've got our services cavity and we've got our internal air tightness. Our 10-star home, we kind of were learning about air tightness at the time, and I think it was 2.7 air changes, even without internal air tightness, and just by sealing under the bottom plate and taking a bit of care, which wasn't too bad. But these days we're around about 1 or less, and we're doing some. This is probably the first home I think we did the eco panel. So very quick. It took 2.5 days to get to this stage with the walls up. 2-story house. Mid floor was CLT and the roof was CLT, externally insulated, which is probably something that is probably going to be the next level. You know, how do we even with a timber frame wall get insulation on the outside if we're going to fill up the wall with timber framing? That seems like a logical place to go, which there's a bit of a trend overseas as well. So and then if we insulate on the outside, then our shonky windows that are in the cold cladding cavity are actually in the right place. So maybe they were actually ahead of their time when they created that window detail that we all love to hate. Anyway, that's that house there finished, and a very quick build, which incidentally Dan Saunders built that house, and then he liked the panel so much he created a company to make the panels, Eco Panel. And then this one here is probably a bit more like Shay and Joe's. So we did a 90 frame, but we actually had a 140 bottom plate so that we could get the fixing cover for the bolt into the concrete, holding the wall down. And then we had an internal horizontal batten for our services cavity and additional insulation. So it ended up being a 140 wall, but with a 90 stud. And that was because the whole site was only 270 square meters. And we ended up fitting a 4-bedroom, 3-bathroom house on that site. And it worked really well. So this is a recent project. I just went around here yesterday. So it's sort of 90% complete. There's still some sunshade elements to go on this lower level, but eco panel job, different builder. James Mackay was the builder. Actually, Damien was the engineer, his company. So we achieved these large overhangs and these high double height glazed walls with no steel. And there's I think one piece of steel in this building, and it's a portal frame over this window on the right with the scaff in front of it. We actually put that steel frame in the services cavity. So, you know, your steel should either be inside your thermal envelope or outside, probably inside. And that's just showing the double height space. And so there's a lot you can do with timber. So a heavily recessed window here and an overhang, sort of an eyebrow. And a lot of the time on a 2-story house, you've got no shading for the lower level. So here we achieved this shading and we achieved this cantilever with no steel. So some engineers like working with steel. Some engineers are really good at working with wood. Others concrete. So we try and limit the amount of steel that we're using in our buildings. And this job here, Eco Panel provided the panels. It was the first time this particular builder had done an airtight job. So we achieved at least, or around about 1, I think, with the airtightness. And then we worked out that if the seals were changed on the windows, it'll be even better. So it might be approaching that passive house standard of 0.6. And a great result for a builder that's sort of new to doing a super home, and a very good builder that just had the right attitude. So I think a good attitude and the right sort of ethos, having the right team goes a long way. And, you know, frankly, you know, I don't understand how, you know, or why we're not all doing simple things like just doing the jib fix framing system. You know, 5 years ago, I thought that'll just become the new normal because it's cheaper and there's no overhead in doing it. You've got more insulation, less timber, so it should be cheaper. But we just keep repeating the same things, the code minimum standards, instead of innovating. And I think, I don't know what the answer is. You know, super home movement, we're trying to create awareness and we're trying to shift this niche that we're working in. I think anyone that does anything different to standard framing is still definitely a niche, even though there's a lot of good people talking about it. We're still in this area of probably about 5% of the market. And you know, it's probably good that people from MB and brands are listening. So we need to work out how to create change.
Well, Jason's details when they come out certainly going to help.
Yeah.
Yep,
so
really,
I mean, the way we've done it with Superhome is with our Superhome tours, and we've surveyed people, and over 90% of people who come on those tours who are building are talking about changing what they're doing and building beyond code. And yeah, hopefully our healthy home guide that Damien mentioned is going to have some impact too. So just finally, we've got our super session, our second super session coming up end of this month, 30th. It's usually the last Friday of the month at 12 o'clock, and we're going to be talking about renovations. So this is a renovation of my own house, which is an earthquake repair. So we're making it more resilient, and we're externally insulating. So we've got a warm roof. We're putting in triple glazing, And this wall here, which looks like a sort of travertine finish, that used to be Hinawera stone. So we've taken the big heavy stone off, which is basically a veneer. You could do the same with a brick wall. We've put ply on the outside of the wall and taped it. And so that's become our airtightness. And then and our bracing, and we've packed out the wall with external insulation. So basically our existing wall with all the services and wiring in there, that's become our services cavity, and our insulation is on the outside. So I'll be going through some of the details of what we've done in that project, and then Daryl Sang from Sang Architects will be talking about an inner fit passive house standard renovation in Auckland, and then there'll also be another 1906 villa renovation. So it's kind of interesting, you know, each different type of house has a different approach. So I'll just maybe hand over to Dan to talk a little bit about what he's doing with eco panels. It's our go-to method, and I really think it's the way forward, off-site construction to that sort of quality.
Thanks, Bob, and thanks all for attending today. Hats off, it's a great thing. The key thing for us, regardless of what we're doing or who we're doing it for, is education. That's our main thing. We want to get out there with, I talk to loads of builders and just potential clients, or just people who are building with other builders, and it's just about getting the education out there. So this is a great forum for everybody. So thanks, Vernie, for putting it all together. I guess probably all of the stuff that I'll talk about, and I'm sorry I don't have any slides, but with the talent that's on the panel, you've covered everything anyway. Just to reiterate what Bob said, that Eco Panel is just a prefabricated version of what you've seen today. It just allows the house to go up a lot quicker and in a controlled environment. So that's our focus with these walls. We're trying to minimise thermal bridging where we can. So it's a bespoke panel. So if architects have a different method they want to put in the panel, or a different design with wall makeup, we can certainly do that as well. So yeah, that's pretty much it, really. I mean, if anyone got any specific questions about it, but I think, like I said, coming in halfway through, it looks like everybody's covered off the performance of these different types of wall panels, so wall systems.
Great. Hey, thanks very much, Dan, and thanks very much, Bob and Damien, for all of that. That's really, really useful. We've got at the moment, just a single question there from Peter Allenshaw again. He says, Bob, don't you think we need to stop using concrete due to its high embodied carbon? So why aren't we doing all our timber foundations for zero cement, all negative carbon foundations? The recently revised Earth Building Standards has a zero cement driven pile footing for under a lightweight wall and details of very low embodied carbon earth floors for thermal mass on mussel shell insulation. First I've heard of mussel shell insulation. Can't even say it. Your views?
So basically, its cost, concrete slab is heaps cheaper than, or quite a bit cheaper than timber foundations. Simply as that.
Yeah. I think I guess the other thing too is you can have some thermal mass, and you can have some underfloor heating if you have a concrete slab. But it is the most common method because of cost. You know, it's perfectly valid to do a suspended floor and have a really good insulated floor as well. And we've even done suspended floors where we've had CLT floors with less piles, less bearers, and we've had a thin topping to put some underfloor heating and some mass into the building. So there's different ways of doing it, and it's like I said before, you know, it's great to see so many different ideas today, and you know, a lot of them are equally valid ideas.
Great. Okay. Thanks very much, Bob, Dan, and Damien. I mean, I just recommend if any of you out there as the attendees have not gone on a Super Homes tour, definitely keep your ear to the ground, follow the Super Homes website and try and get on one of those. I've seen some of the homes and been on a number of those tours myself, and it's just great. And it's really, what I love about it is watching 30 people walk into a house in Christchurch in the middle of winter and look amazed because it's warm on the floor, and they can take the jacket off and it's comfortable, and we're just so unused to living in warm, comfortable houses. So it's really great that you guys showcase that. And thanks, Dan. Dan, actually, what I didn't mention, he helped to build the Beacon Pathway high performance home in Hive all that time ago. We got some great R values out of that as well. So yeah, thanks very much. I guess you're the panel expert on the panelists. So
we did following on from that, from the warm frame, we did probably 4 other jobs using the same system, and the clients were just amazed at how well they performed. So it turned out really well.
Excellent. Well, very glad to hear that. Okay, thank you, super homies. Now we're going to move on to our last presenter from Canada, although talking to us from Auckland, Sean McIsaac, who is part of Oculus. And for some of you, you'll need no introduction to Sean. He's very well known in LinkedIn circles, at least, for steering all kinds of excellent trouble with a number of really thought-provoking and insightful articles. So I really like listening and hearing Sean and the other guys at Oculus. They're very active and passionate in this space. They've got a great website with really good links to all the significant work they're doing. So I saw a presentation from Sean a couple of weeks ago, and I just knew they had to be involved and part of the kind of solution that we've got here. So what I'm keen for Sean to talk to us about is some of those medium density type solutions. Okay, over to you, Sean from Oculus, with a beautiful pink shirt.
Thanks, Bernie. Yeah, as Bernie said, so Oculus, we're facade designers, building enclosure designers. Sometimes we do lots of different things, but a lot of what we do is design mid-rise buildings and apartments to be warm, dry, and healthy. We're working on tons of these at any given time. And as the company's evolved, we've gained some more trust with designers and builders and clients and been able to do some really exciting things. And to the point where I'm actually kind of optimistic about what we're going to be doing in the future. If you ever invite me to speak, always put me last, because I usually do my presentation while I'm watching, so I get to fact check everyone as I go. I'll do this really quick, and you can email me later if you disagree, and we'll have a good battle about it. But Nogs do absolutely nothing structurally. They do nothing. You can hang cabinets on them. That's all they do. You can definitely, you do not need to do them already within the existing standard, 3604. Go ahead and do it, no problem. The only thing Nogs do is help you lose heat in the winter. This research that you're doing has been around for like 4 decades. So in 1974, I've not been able to find this publication. If somebody has this, it looks like exactly what we're talking about today. So 46 years at least of talking about why are we building with dwangs and walls. And this basically says there's no benefit at all, and everyone totally agrees. Little disclaimer on what I'm going to be talking about. So combustible materials, you cannot use timber in buildings over 10 meters tall in New Zealand under the acceptable solutions. We don't know why people are doing it, but they are. So something to keep in mind as I'm talking about apartments. Operational versus embodied carbon. I've yet to pitch a benefit of embodied carbon to any client because there's no money in that, but I can pitch energy savings, so it's not insignificant. Greenhouse gas emissions, this is some Australian data. It might be different in New Zealand, but actually plywood has a higher carbon content than fiber cement bracing, so it's something to look at. And I've got really good news on window thermal psi values. I can speak from firsthand knowledge that every major window supplier is working on passive house compliant windows, and those should be coming out next year. So really good efforts in the windows sector to improve their efforts. I'm going to talk mostly about one particular case study. It's a 5-story building. It's about 40, I think about 40 units in Auckland. And I'm really going to focus in just on this one particular wall section here in the middle of the building. It's just got some kind of regular punch windows, and I'll take you through a little bit of a thermal analysis of that wall overall. So we've got 145 square meters of wall. Of that, the floor slab is about just under 6 meters of that. Timber framing, about 51 square meters of that. The glass, 15. Window frame, another 11. So you add all those up, it kind of looks like that. So we've got about 60 square meters of insulation left. So a lot of pink, a lot of green, a lot of orange. Looking at the areas of these, this is the percentage area breakdown of each of those. We've got 35% timber, we've got about 40% of that wall is insulation, and about 18 combined with the windows and the glass, which doesn't look so bad. We need to actually look at what are the R values and U values of these frames, look at how much heat loss is through each of these parts. So when we do that, we find that all of the big parts of the wall, the insulation, the timber, well, they make up a large area component of that wall. They actually now make up a very small part of the heat loss. And what we find now is that actually the windows are 61% of the heat loss of that wall. So, yep, let's focus on reducing some framing ratios, but let's not forget that this is where we're losing all of the heat. The frames, just the window frames alone on this particular wall is 31% of the heat loss. So a third of the wall is being lost through 8% of the area. So really important to keep things in perspective. I get this question a lot. How much does it cost to build better? What can we do? If you look at, these are the types of framing we see on our sites. These are 300 centered nogs and studs for no reason. We don't know why it's like that, but that's all right. We'll keep working along. The question really needs to be is what is your target value? So R2.0 is what we're trying to get to. We've got the Beacons research showing that what we're actually building is more like a 1.57. So what would we have to do to a wall to get to an actual R2? So if we did 140 timber framing with R3.6 insulation, just over that R2.18, that's cool. We'd meet our target, except we've got concrete slabs in mid-rise buildings and need to account for that effect. And so you're actually maybe R1.3, so you're below what we're trying to get to. So then the question is, well, how thick do we need to make the timber to make up for that concrete slab bridge? You can see in an internally insulated conventionals with this concrete slab coming through, you're breaking up, that's a thermal bridge as well, and much more conductive than timber. You'd have to increase your wall thickness to 240 framing to account for the effects of that concrete slab. So you're ending up with about a 300 millimeter thick wall to achieve your R2.0. That's a very, very, very thick wall. I've never been able to convince anyone to build that yet, let alone all of the condensation problems that thick a wall would have in any part of the country, not just the cold parts. I don't think this would actually work for R3 without some vapor control considerations and air control layers. Here is where exterior insulation solves all of the problems we've been talking about. You can just sum up all the research you're about to do, Vernie, and just say, well, let's exteriorly insulate and not worry about any of it. Bob mentioned this is a trend overseas. It's a trend here too, and it is exponentially growing. There are lots of people doing this, and for very good reasons. Our conventional way of breaking up a 140 steel frame is with a thermal break, we'll call it, which is a 10 millimeter strip of EPS, which really does nothing for thermal bridging. It's very poor. Even 140 timber is not too bad. But you look on the far right at a 63 mil stud with continuous polyiso, and you've got 100% effectiveness. You're getting every bit of insulation that you paid for instead of just 23%. Next question we get, how do I attach the cladding? Here's 8 examples. I can think of about 28 examples of how you would fix insulation, depending on what type of cladding you want to fix. how extravagant you want to get with your clips. But there are lots of ways to do this. I'd be happy to help anyone through that. It's very, very simple. Here are some examples of ways people are attaching clips. You can fix right through it. You can attach it on the outside. You can build sandwich panels. There are lots of ways to do this. It is very, very simple. And here are buildings that are actually being built with exterior insulation. From top left, it's the City Mission building in Auckland, all CLT with exterior insulation. Aroa Street, a built for rental apartment building. A couple others there, and that top right one is the Mount Smart project, which I'm going to keep talking about. In the bottom right is the Grays Avenue project with Kangora. Very large project, all exterior insulated. Actually a very fabulous building from an energy perspective. If we were to do R2 continuous, so back to our example, we're trying to hit that R2 target. If we did 75 mils of a rock wool, that's R2.25. We might have some screws through that, maybe some flashings. We're hitting our R2 target, no problem. We've got no slab edge bridging to account for, and our total wall thickness, just 225 versus the 300 if we were to conventionally internally insulate it. So you see it's actually a more effective from a space-wise, and I'll show you how it's more cost-effective. That's why it's more cost-effective, because you can use 90 mil framing instead of 240 mil framing to get the same energy result. So it's being smarter about where we put that insulation. Instead of trying to account for the thermal bridging, let's just completely defeat thermal bridging. We can flip this argument the other way. Let's say, what if we match what the industry standard is doing? So we build a 140 frame wall, we account for that insulation, we've got about a R0.93, or we could just do continuously 30 millimeters of mineral fiber with no insulation in the studs and get the exact same result. You can use any framing you like to do that. Does it cost more? So this is a very specific, very real project. It's just finishing the consent process right now. That's what the slab looks like. So it's got a continuous insulation past it. It's all exterior of the framing. Cladding's held through the insulation. So this is what the slab looks like. Those tricky inside and outside corners, when we've got continuous insulation, there is no studs to account for. There's no extravagant framing required. You can literally do whatever you want on the inside. We don't care. So originally specified, 140 timber frame wall, and that would be about 1.3 and about 195. And the solution we've come up with is a smaller framing, so we can get closer packed studs, but 200% better than what was originally proposed. And it saved 3 months on the project, which has a very real cost impact and a real benefit to the client, of which some are listening from Kangora. Hi, guys. So you can see that this is a very real thing happening. The main savings to this project was from faster close-in times and being able to work insulation and electrical trades at the same time. This particular example was metal framing, allowed a closer, didn't have to wait for timber to dry before linings got applied. So like I said, this doesn't cost more, it's just different. So there's my number, there's my email. I'd be happy to chat on anything you like. Please don't hesitate to do that. Cheers, thanks.
Hey, great. Thank you so much, Sean. That's really super interesting. And again, some really compelling information there for anyone considering medium density or even, smaller houses. But yeah, really great. I loved, only you would come up with a slide on the fly as to what we missed in the earlier speakers. So that's really great. Thanks for that. I'll go back and look in more detail about that. But it's great because it'll help to inform this whole ongoing conversation. There are a couple of questions that have come in. So this isn't necessarily a question, but you might want to comment on it, from Peter Allenshaw again. He's saying that Andrew Alcorn and his PhD thesis, Global Sustainability in the New Zealand House from Vic Uni 2010, found that in New Zealand situation, plywood's net negative embodied carbon. He's got a lot of other New Zealand specific embodied carbon values in his thesis too. And yeah, he's well known, I think, in New Zealand for coming up with lots of those embodied carbon.
Yeah, could be. I think the point of what I was trying to make is that the idea that some of our thoughts on what is high or low embodied carbon, you really actually do need to work through that to understand the specific supply. So you can't just apply a generic idea of embodied carbon and think that what you're buying is going to be the same on your project. So you can't just say that as a blanket thing, this is going to be better. You need to actually run it to ground and find out where that specific product's coming from.
Yeah, absolutely. Hey, thanks for that. Liz Ross is asking here, oh, it's been answered by somebody. Is external insulation a good idea for retrofit scenarios and renovations and that sort of thing? So I'm just wondering if you have a view on that.
It is an awesome retrofit example or option. We are doing some of this right now in Dunedin with Kangaroa on some existing star block projects, existing big concrete blocks, 50, 60, 70 years old. They needed some work, and looking at how do we improve those the best way possible. John Davies in our office is looking at a master's program, and the results of that master's program should be, or what the plan is to have actually a verification method done for externally, so external insulation retrofits. So the idea being that you keep the existing cladding in place, you install external insulation over top of that and reclad over top. And we'll be testing that and verifying it to the building code requirements so that anyone will be able to use that, that method for their building compliance path, which is a really exciting opportunity.
Yeah, great. Thanks, Sean. I see on the chat there that Bob's highlighting the Super Reno session for anyone who's interested in renovations using those external insulation systems. I can't see any other specific questions, so please, all of you attendees, if you've got any specific questions for Sean, now's a really great time to raise them. I did have one question around, I thought it was really awesome that you highlighted about keeping windows in perspective. And what are you guys, what's your go-to in these situations for the windows?
So a couple tips you can do is you want to maximize glass to window ratios. You want lots of glass versus lots of frames. We tend to see a lot of people breaking up very small pieces of window. You're just creating pathways for heat loss. Thermally broken frames, even the lousy ones we have on the market are still better than nothing. Placement of those windows, bring them in line with the insulation. Many of the manufacturers now have standard details. They'll help you through that. It is being consented, much better ways to do it. But yeah, in general, those are kind of the tips. Minimize your number of operable vents. Operable vents have extra frame material, so you want to get away from those. And maximize your glass sizes. Don't introduce extra aluminum for fun.
Okay, that's always a good tip. Don't introduce extra aluminum for fun.
And the timber, don't introduce extra framing for fun either.
Yeah. None of it gets put in there for fun. Okay, we've got I think this is more comments from Adama Black again from Jib, and he's asking their comments on active ventilation when using closed cell insulation, even RAB where building is so airtight. I mean, obviously that's going to be different in a medium density situation, but do you want to just give us some comments on that?
Yes, so back in 1970s, 80s, there's lots of research from very good people at brands saying that you need to mechanically ventilate and heat buildings to prevent mold growth. That was in every research paper for the last 45 years. It's never changed. And it's been reinforced recently from brands. So they're now suggesting that apartments are too airtight to ventilate with windows, which is something we've known for 40 years. So good to see that brands is catching up with their own research. It's pretty good stuff. You have to mechanically ventilate buildings. There's just no way to do it unless you are a very smart person like Jason, and maybe Jason wouldn't even do it. It's unlikely that you'll be able to predictably ventilate any building just relying on opening the window.
Okay, that's an interesting viewpoint, and I think we're going to have more discussion on, because again, yeah, I think there's also some of those passive approaches and teaching people how to ventilate their buildings properly if it's a smaller scale, but definitely at that medium density, you start to get.
No, I agree completely with Sean on that, since he brought my name up. Yeah, so he's got it right for every size building, and as the buildings get smaller and simpler, it becomes more important to mechanically ventilate them, not less.
Okay.
Yeah, no, there are ways to passively ventilate buildings, but it's not a window. It's much more complicated than just opening a window.
Right. Okay. We're not going to try and divert this into we'll have another seminar maybe on ventilation systems and all of that. But Joe, I see you there listening in. If you wanted to kind of unmute yourself, because I'm just conscious that your house has no mechanical ventilation system, and can you tell me a little bit about your IEQ there? If you unmute yourself. Yep.
So we don't have a whole house ventilation system, but we do have mechanical extracts in our bathroom, kitchen, and our laundry. The one we have in our laundry is a Lunos system, so it's got a heat exchanger in it.
Okay.
And the air, so basically the heat exchanger means that you get very little heat loss from ventilating the space. And probably if we'd done it again, we probably would have put the Lunos in the bathrooms as well. But yeah, we don't have a whole house system. We did look at it, and it was quite expensive at the time. I don't know whether we'd do it these days. Probably, we'll probably think about doing a simple system these days. But you know, most of the year we have the windows open, so we don't need to ventilate. And actually, it's probably only about 2 months in the middle of the winter where we find we're not opening the windows. We don't have the windows open regularly. Yeah, so that's when you really need it. It's that middle of the winter time when it's just not warm enough outside to open the windows.
Sure, thanks, Joe. And I know the good people at the Home Performance Advisor and Vicky Cowan, who's co-hosting this, will be cheering in the background, saying that just that blast ventilation twice a day, 15 minutes. You know, there are ways of doing it in an actively managed way, but yeah, I say I don't want to take us into the ventilation space too much.
And you know, I work from home, so I'm at home ventilating the house through the day, whereas so a lot of people aren't home, so they can't do that.
Absolutely.
You can do it in 5 minutes in Wellington.
It brings up a good point though, Vernie, and just the last point on ventilation is that the whole house has to work together. You can't just flick on one thing or put a vapor control there and think that you don't have to do other things. Framing ratios is one part of a much larger discussion on, do we want to build things based on evidence and want to actually build things that are realistic, or do we want to continue pretending that the way we build things is actually quite good?
Yeah, okay, interesting point. It seems like we've got more seminars to come on all of these subjects, so that's really that's great. We can probably run this weekly. Hey, listen, we're probably going to have to round this up now because we're determined to try and finish by 12:30. So I just wanted to know if any of you panelists had any last comments that you want to just throw out there. I'm getting shaking heads from my panelists, so that's all good. Hey, listen, just a few final kind of things. Firstly, I'd like to just thank all of you attendees for maintaining the distance and sticking out to the end of this. It's really great to see such a level of interest, and we've had quite a bit of chat coming through that seems to suggest that they've really appreciated all of the content. So panelists, thank you very much for your amazing input to this session. We usually follow up one of these with the traditional kind of survey to see from all you attendees what you thought of it. Please fill that out. That will enable us to work out any technical glitches and improve the next time we run a seminar. And I think we may try and run some future seminars, certainly based on the results of the first stage of the wall research, but also maybe even covering off some of these other issues that have come up today. A recording of this whole session will be available to everyone, as will a list of the questions and answers, and we're hoping to provide a little bit more detail on some of those answers for you in the form of sort of show notes that will give you links to the panelists and some of their information on the basis of today. So that might be on the Beacon website alongside the video as well. And so, yeah, that's probably the best place to look for that, is on Beacon's website. And look out also for some upcoming seminars and discussions and the kind of consultation that's coming out, particularly around the building code from MB and the Buildings for Climate Change program and all of those things. I think we're in a really good space to be looking at this issue, particularly the thermal performance of our buildings at the moment. I've got a lot of optimism. We've got some great attendees watching this, from great team at Brands, great at MB, people from Kāinga Ora, industry people out there, companies. I think really this has all been about collaboration and a collaborative effort moving forward to find solutions to these problems. As we identified, I think, in our original research, you know, there's no one source of blame. There's no point in finding blame about this. It's really about how can we all come together to collaborate on an effective solution to provide the best framing and the best thermal solutions for New Zealand. So thank you all very much for being part of that collaborative approach and joining with us today. So that brings us to the end of the seminar, and I look forward to engaging with all of you, attendees and panelists, in the discussions that follow. So ka kite anō from all of us, and thank you very much for your attention today. Haere rā.